talking about microprocessing theory.
Yes, I would like to bring you some things about lessons of theory. People are emphasizing some problems of the theory. Yes, I will also review something about lessons of theory at the beginning. At the end, I would like to say something about new results. How some of these problems can be avoided. Situation is not right here. I will play. Okay, so the point is that standard formulations of string theory are perturbative and on-shell. So what you read in textbooks is on-shell and perturbative formulation, which of course doesn't mean that we cannot speak about non-perturbative and off-shell effects, but the point is that, especially using symmetry, but the point is that usually it's done in indirect way, either by using sort of dualities, which can be involved like CFD, or using properties of supersymmetry, some normalization theorems, superrarities, and so on. But to directly address some very important questions like this landscape, so the structure of vacuum of string theory, probably one would need formulation of string theory, which is first of all off-shell, non-perturbative and background independent. Compare the situation to situation in quantum field theory. For example, what is the standard string theory would be knowledge of, let's say, Feynman diagrams, but only on-shell. And what is, of course, off-shell formulation is quantum field theory. So not that we can get a lot of results in quantum field theory which you cannot from on-shell Feynman diagrams only. Of course, it is easy to say, but how to do it? So the most straightforward way, and the first one historically, was then to apply basic logic of quantum field theory. So quantize the theory in, let's say, most direct way, how we do it in normal quantum theory. Of course, maybe it is not the best way, because you know, for example, that maybe string theory is also some effective theory of some more dimensional, 11, 12-dimensional theory. So I'm not claiming that string field theory should be a final theory of string, but at least maybe it is some effective theory which is of shell, so which can give some more results than standard string theory can do. So I will discuss here open bosonic string theory, basically the whole lecture. And for open bosonic string theory, this philosophy is using this philosophy, one thinks Witten's cubic open string field theory, which was written by Witten in 1986, and which I will call open string field theory. Keep the name to distinguish it from the string field theory. So, what is the procedure? So you say that there should be some functional on the space of string configuration, which is sort of wave function, so it's sort of like a Schrödinger representation. And of course, one needs an action, and then the claim is that this action is going to give perturbatively to give a standard string theory of strings. So, of course, it's not visible immediately, but the structure is suggestive. So you have two terms, let's say kinetic term and interaction. And if you neglect interaction, you obtain something like this. Q is a BRST charge. And what is the classical equation of motion? Well, it is a Q psi equals 0. Basically, it is defining the definition of states of the theory. So the cohomology. So this is going to give normal string states. Okay, to define this structure completely, we have to say what is this star and what is this integration. And one can see that, it's not written here, but that star, which is a Witten star product, which should not be confused with Royal star product, is obtained that you take two string states and then overlap two halves. So put it together and integrate over all two iterations. Say that it's mathematically something like this. And integration, this formal integration, is simply to put two halves of the strings together and then to integrate over all configuration space. This section will have a gauge symmetry, and this gauge symmetry that is huge. This one can be any also configuration of a lower ghost number. So this is the, let's say, the most visual way to describe it. But for practical purposes, it is better to represent psi not as functional, but as a state in the space of open string states, but of course off-shell state where the momental states can be anything. So you can see that string theory can be imagined also as an infinite collection of fields, also normal fields. But when you plug this representation into action and calculate the action for this infinite collection of fields, you are obtaining that it's a non-local theory. As expected, because we know string theory is not a quantity theory, local quantity theory. Okay, there is a generalization of this idea. One can define this structure algebraically. It's not important to be taught here, but just to mention that this generalization allows to address allow defining the string field theory on other backgrounds and not the standard background of open strings. So we can put some range inside and maybe define string field theory with this background. And so there is some bracket, and there is some star, and there is some operator few. These properties are necessary. These first three properties, for example, guarantee gauge invariance conciliation and other sides, the consistency conditions and to define the string theory. So we are going to start at this standard string theory, and this algebraic representation can be written in the following way. So the star is simply, okay, first of all, this bra state is a BPZ conjugation of the state. And this BPZ conjugation is basically very similar to condition conjugation. The only difference is that there are some sign factors and the order of the operators. Straightforward. And the star then is obtained by contracting this free string vertex given in this way. So okay, this B and B tilde are simply C number matrices which has all these indices which A simply C has. So there's a level index and also there are free fields of RS goes to 1 to 3. Here is the ghost part. So there is a metric part and the ghost part, and they are separated, factorized, which is very important. And also one thing that it is very convenient to use the Feynman-Siegel gauge, which is defined in this way, that the zero operator.
Completely some heredity. We do not have d dagger n equal d dagger b minus n.
Well, heredicity in which sense?
We impose on the operator some heredicity of alpha and d.
It is a positivity in some sense, but something which gives positivity to the action and the heredicity. So this gauge condition is completely okay.
What's the necessity of squeeze? What's the necessity of squeeze?
Of squeeze state. The point is that, well, it is sort of easier to understand why this vertex operator is squeezed state. Squeezed state means that, say, you quadrant of the level raising operators, creation operators. And the point is that what is the start product? I told you that it is putting two strings together. So we have a delta function in functional space. And delta function in functional space, and write it in oscillator representation in discrete state, like for a harmonic oscillator. So that's the question. So you would expect it to discrete state. It's how people found this representation. It's very hard. So using this open string field theory, people arrive to some really important results and some important properties. First of all, what is interesting is that when one analyzes perturbative expansion of this theory, so it should be equal to the open string theory, you obtain that it also contains all virtual closed string states, which is not very trivial as may sound, because you know this open and closed dualities, but it is not really completely so there is a possibility that open string field theory also describes closed strings. But of course, how to define closed string operators, that is another question. Maybe one needs knowledge of quantum theory of this and just taking off classical properties. And then it was used to analyze famous sense conjectures and to repeat them. So sense conjectures were conjectures about the structural vacuum of string theory. And first conjecture is that the thing that we have a tachyon in open string theory does not mean the theory really is sick. But the point is that we are expanding around false vacuum. So the situation should be something like this. There is a false vacuum in which we are expanding, and there is some tachyonic field, always some tachyonic potential. And then what happens is that there is some true local minimum of the potential, let's call it a true vacuum. So it is not really a true vacuum for this theory, because it is like phi-free theory, probably not well defined because of also closed string tachyon, but in superstring theory it can be. So basically there is a true vacuum, and this is not a vacuum because we have a D25 brane inside filling all the space. And the tachyon simply represents the instability of this brane. And what are other branes? Other branes should be solitonic solutions of this effective theory. And the third thing is that we expect that because tachyons condensate here and do not have it anymore, that this physics around this vacuum, at least locally, is described by closed excitations only without open string excitation, because there is no any more D-brane, so open strings cannot attach to nothing. So, and really, a lot of data accumulated in the last 5 or 6 years, which give really evidence in support of this sense conjectures. But, so, first of all, one should see that string field theory was used to define, to connect and to describe different vacua of the theory, which is really something very nice and looks promising that this sort of a theory can really be used for non-perturbative descriptions which are of shell and boundary and background independent. This is important idea. So we started from one background and went to another background, non-perturbatively, using the same theory. And people could estimate the different exotic energy of these two states. However, I said evidence, not a confirmation, because first of all, nobody found any analytical solutions of real physical significance in the open string field theory. So all these results were done numerically using level expansion. So what you do, you cut the string field. You use only finite number of fields in this instance expansion and then calculate. This expansion is, in fact, not well under control, and in fact, why it should be convergent at all is basically a mystery. And what appears that it is working when you roll down from the vacuum to this true vacuum, but when you start to go up, for example, to analyze, let's say, some background which has 2D25 branes, which has double energy, and start to go up. The point is that this expansion immediately breaks down. This is this even genetic property. It appears that whenever you go up in energy, even marginally, just to shift the brane adiabatically, expansion breaks immediately on the length of the string length. So there are, it is in some sense expansion, so in some sense perturbative, these results, and also, on the other hand, this expansion is a problem, and you cannot address all backgrounds you need. So the question, of course, is it a problem of level expansion or something deeper? But so the problem of open string field theory. Well, first of all, it's hard to answer this question because people only know to do level expansion in open string field theory. So what should do? So one idea is to say that maybe it would be more natural or better to define the theory around the true vacuum background and not around some false vacuum. This is going to make things better. But so how to do it? Well, at the beginning, things look easy. So one can shift. Suppose that we know field of this, let's call it the true vacuum, and then we shift the field and put it in the open string field theory action. And what is nice that what you obtain is the action of the same type for this new shifted field around the true vacuum, which is also gauged in Banja. And but that this kinetic term has now new, let's call it a BRC operator, which is defined in this way. So why not to do this, try to do this? Well, the problem is that you should know first of all this vacuum psi 0, and you know it on the level of expansion. Okay, then you can say, okay, I can use this level of expansion as an approximation, or try to fit something to this level of expansion. But the point is that when you do shifts in string field theory, this is really a thing which is happening very frequently. It is why people are confused on many different points in the last years. Is that when you shift when you make a shift to obtain, let's say, the best form, usually, or some natural form, either for Q or for states, you also need to do non-trivial field redefinition of the field. And so, how you can do it, how this field redefinition appear. You can analyze, for example, this type of field redefinition. So you multiply psi with exponential of some operator, and this operator has this simple property, easy to construct operators in this way. You can show that the action has the same form for this new field, which is redefined, redefinition of the previous field, so it's nothing physical, it's just a redefinition. But with a different kinetic operator. And in fact, this different kinetic operator can have completely different form. This Q hat and Q tilde can be completely different. For example, so Q tilde can be very complicated, but maybe with some field redefinition can be put in some very simple way. So for example, if you look what is level expansion giving to us, it is giving some complicated operator. But it doesn't mean that all operators, that it is the fact for the theory. Maybe there is some field definition which puts this operator in some fine, nice form.
This is supposed to be dictated by true value.
Yes. But you see that using this field definition, you really cannot play with level expansion. Probably this definition needs the whole expansion of the field. Of course, it is different. But the situation is that you cannot do much in this way. You cannot improve things. You are going to obtain, if you use this level expansion, you are going to obtain very similar theory, but again with the same problems. And then the option is to, another option you can do it analytically, or anyway, you can try to guess. And that is what Prester and Silva did. In fact, if we believe in SEM conjectures, then we can use them together with these properties of the theory, like gauge invariance, and try to guess this SEENET operator around the true rate. And what we can use? Of course, gauge invariance, because still the definition does not change gauge invariance stays. Then, if we believe that in this first SEM conjecture that there are no open string excitations around the true vacuum, then Q would have to need to have a vanishing cohomology for Fock space. And then there is a third thing, not that immediate like previous two, but very important, is the concept of universality. We started here from string field theory defined around B25 range, but we could start from any other background, like two D25 rings or D23 rings or any ring, any number you want. And we could also roll down in principle to the true vacuum, and then we should obtain the same theory. But you see that these different backgrounds from which we use the start, they have different method content. So basically the most comprehensive way, or the easiest way to have this universality for all backgrounds is that for Q you use only constituents which are general for all these theories, and this goes. So the conjecture of Prester says that for this vacuum string field theory, all guessed conjecture and the true vacuum, it should look 10 minutes. It should look the same, but with BRST operator, this kinetic operator, which is purely ghost. And this is, if we accept this, and using gauge invariance and these other properties, opposite form than for this Q. So, Q is basically uniquely done if we accept these properties in this way. But you have to notice one thing here, that this Q defined in this way can be written in the operator form in this way. So Q is a local operator insertion, and where exactly at the midpoint of the string. This is really delicate. So you represent string in the half plane. Circle of radius. So this point I is here, and this is basically the points when you are in free string product, this star product of free string fields, they join. So this can be very similar and really easy. Okay. What are the properties of this vacuum string field theory which are better than normal open string theory? Well, it is that the equation of motion factorizes in gauss and method. This is very important. So these are all details, but the point is that we can solve separately the method and the gauss part, and basically we can write it in the way that there are projector equations, like this equation 1 here. Gauss can also be put in this way, in this elaboration. Okay. And also using Siegel gauge, this kinetic term is very simple. So, idea to check is it really a good description of string is to find some, starting from true vacuum, find some states or some backgrounds which we know that exist in string theory. So, first of all, what is most simple? It is this space-filling B25 ring. Can we find an analytical solution for it? Yes. It was done by Serbia and it has this also squeezed state form with some metric speed. And when you plug it in the equations of motion, you obtain that this P should be equal to this product itself, and this product is defined in this algebraic. So you have to solve some complicated algebraic equations, and these matrices are all infinite dimensional, and possibly P can, there is no reason why T should commute with these other matrices. And well, if you accept that, if you conjecture that P commutes, then you obtain what is called a sliver solution. Katakana, because this solution defined by B25. So it is a squeezed state solution, very simple. Norm is given in this way, and the energy of this solution is also in this formula. And what is important is that we can construct other, 4 years ago, other BP brains, quite insane. These are just the details. And that these states have really this, what we need, that the energy densities, ratios of energy density between different branes are given correctly, well, by the relations we expect in string theory. You can also multiple brane solutions were found, etc., etc. But this all is very nice. But this theory has huge problems. And we can group it in 3 different types. First of all, there are singularities of sliver. Well, when you analyze this what I showed you on the previous transparency, these normalization factors and energy, is N25 and E25, and you analyze these determinants, it appears that they have 0 modes and they vanish. So normalization factor vanishes. It's not that bad, but the energy density vanishes. So I said that the ratios are okay. So what you need to have proper description is that this coupling constant which appears in the action should be infinite. So that this theory needs some normalization, which is not really expected. People like string theory because they say it is finite. So this is not good. And then also there are some technical problems with equations of motions and constructed Fock and non-Fock states that it cannot be at the same time.
What do you mean by non-Fock states?
So non-Fock are, let's say, these theories. They are not Fock. Of course, we look for the ratio. They are going to be 0. Then, the spectrum of fluctuations, you can analyze the spectrum of fluctuations around, let's say, B25 brane, and of course you have to obtain standard open string theory, but you do not. You obtain states with correct masses, but for conditions for polarizations are not okay. For example, vectors have not have a position at all. In the high states, you obtain only states of high spin. And so, and the third thing, which is quite interesting, is that this theory does not have scale at all. There is no basically coupling constant. Why? Because you can find the field with definition in the same way you do before, but if you choose this operator in this special particular form, where gamma is some number, action is going to stay the same, and the only coupling constant is going to change. So if you put gamma equal to k, you know k is equal to 1, or to k is equal to anything you like. So this theory does not have classical scale. We know that string theory has a scale. It has an open string coupling. So this is the reason why this vacuum, Castelli-Sensica version of vacuum solutions in field theory was considered to be, let's say, very similar and maybe not physical. But in this having no time at all, I have to say something about these two results. And now I do so fast that nobody's going to understand it.
That's the trick.
This is the trick. Good lecture. So, can we find, so these first two problems can be settled only if we find new solutions. So we say this solution is simple. It's not good, it doesn't represent any physical, we need new solutions. But to find analytical solutions, even in much simpler theory, obviously it's not simple. And again, these sliver-like solutions have this nice property that ratios of tensions are okay. There is something good in them, but not all. So, what we analyzed is that we called it the dressing of the state. So we analyzed state of the same form, it is a squeeze state, otherwise squeeze state within hard to solve equations of motion. With the same theory should be epsilon. But with some correction, which is given with the tensor product of some vector here, and three parameter epsilon. This psi and kappa are bounded in this way. You can see this immediately. Of course, this new T matrix does not commute in this mathematics theory. And what one can see is that using this as an ansatz, one can find three solutions of the equations of motion. With epsilon 0, this is the old sliver, epsilon 1, and epsilon this range. So analyzing these three solutions, one can see that first and third are sort of a dual. You can in fact rewrite, reparameterize this epsilon to something different and obtain that this is in fact 0, 1, and infinity. And this algebra of these epsilons defined through a this product is given in this way. So epsilon nulla and epsilon k plus 1 over k are sort of sick, but this epsilon equal 1 is sort of a special. And why it is special is that when you use this solution in equations of motion, and then in action, in the expression for energy, contains this additional factor. This factor goes to infinity. So you can use this, you can scale epsilon to destroy this infinity of normalization factor and to obtain finite action with finite Hartley velocity. And this is basically the idea. And the second idea is to, using scaling, you have some scaling factor. And this factor basically plays the role of the scaling theory. So it is in some sense dynamically generated, which, because of this previous property of the classical theory, we knew that it should be somehow given, and that should be the quantum theory, or something like this. So, the big technical details are very involved, and these papers they go together 8 pages. But results are that we can, like before, find all these interesting states, like DP brains of different dimensions and different numbers, and basically the scaling can be used to cure all these problems. And just this is not time to be on there. But of course, there are some open questions which I'm not going to discuss. I think through the questions of thank you.
Any room for causality in your axiomatic framework?
First of all, questions of any question concerning geometry here. Of course, this
your first transparency where you put weak connection, you put on the bottom line, the expansion of the string field is ordinary fields. So I expect that if you do the integration, you will obtain big monomials which commute.
Yes.
So do you have something directly at the level of the string field? That's the question.
You can analyze this in a way, yes, like this, analyzing this fields, the number of fields. This field is not local, and it's very hard. For example, in level expansions, you're going to obtain something, let's say,
You know, in ordinary ones, you cannot do it.
but here is something similar. It's very similar to non-computer theories, because this product is very special. It is nothing which comes from string theory. But this is very hard to address, anything which is especially in all string theory. Because we don't know what to show. You cannot describe closed strings.
Regularization that you introduce is your final result independent of one value? I get the impression that it's true only for a particular value, epsilon equal to 1.
Yes, but that is the point. I'm analyzing classical solutions, and in this way, you can make 3 classical solutions. And the only one which appears that is empirical, which can avoid singularity, is this which goes to epsilon. Is epsilon equal 1.
I understand that, but when you introduce a regulator, you would expect that your answer should be finally independent of what regulator is doing.
I think I don't.
If you introduce a regulator, it's something arbitrary. Final result should not be independent of, should not depend on the particular value of the regulator.
Absolutely. But this is the point, is that there is some scaling factor. But you need a scaling factor. Because this scale, which is put classically in front of the action, can be killed by field.
Epsilon and its scaling, it's not dimensional.
I mean, if it goes to 1, with some. While these things are 0, let's say action, because this determinant has some singularity which can be analyzed, let's say, in level expansion, and because they have terms of this type. So L goes to infinity, this goes to infinity. And then 1 minus epsilon, you can put like something like S to L to X, and then to prove this is 0. It goes, okay, because it goes down. So this S is basically something which is free. But you need some parameter which you're going to define as a coupling constant in the scale.
Do you get the scale of the
Yes, then the scale is connected because it is proportional to the energy of the T25 brain, and you could say the T25 brain is like this scale. Like dimensional regularization in some sense.
Okay, so let's thank the speaker again.